The skin is full of contradictions. It's soft and sensitive, but also tough and resilient. In fact, it's self-healing. It's both the barrier that protects us from infections and our most intimate connection with the outside world. Today's guest, chemical engineer Zhenan Bao, has spent the last 2 decades reverse engineering the skin's many remarkable properties in order to create wearable electronics that are just as soft, flexible, and versatile as the skin itself. Bao envisions a world where stick-on devices could help heal injuries, manage anxiety, and even enhance our perceptions. And soft, implanted devices could give neuroscientists new insights into the workings of the body and the brain. In today's episode, we talk about what makes the skin such an intriguing problem for an engineer like Bao, some of the many applications of her technology for medicine, neuroscience, and mental health, and its potential to enhance or extend our perceptions. This is From Our Neurons to Yours, from the Wu Tsai Neurosciences Institute at Stanford University, bringing you to the frontiers of brain science. Zhenan Bao, it is great to have you on the show.
Thank you.
So there's a lot I would love to cover in this episode, particularly some of the amazing applications of the soft, flexible electronics you've been engineering, from implantable sensors to wearable tools to help with mental health. But first, I thought it might be good to dwell for a moment on an image that you put in my head the first time we spoke, because I think it'll help us visualize some of the amazing things our skin does that you've been working to replicate or even improve on in your lab. The last time we talked, you mentioned that when you were starting your chemical engineering lab at Stanford in the early 2000s, after many years working as an engineer at Bell Labs, you were inspired by this sort of science fiction vision of a perfect artificial hand. And I always picture the prosthetic hand Luke Skywalker gets in The Empire Strikes Back. Can you tell me a little bit about that idea and how it inspired the direction of your lab going forward?
Yeah, so as a chemist and also an engineer, when I think about skin as a material, it's flexible and also stretchable, can biodegrade, as well as can heal itself if there are wounds. On the other hand, skin is the organ which can sense temperature, sense forces, and allow us to explore the surroundings and know what object we're touching or interacting with. So I think about it also as a sensing system which gets stimulated by external environment, but then convert the external stimuli into electrical pulses that can be used to communicate with our brain. So I've been fascinated about skin in these 2 very abstract functions.
Sort of its texture, its stretchability, and its sort of self-healing properties as a covering, and then also its neurological properties, the way it senses, the way it communicates.
Yeah, exactly.
So it sounds like you saw the skin as sort of an engineering challenge. What are some of the most challenging pieces for you as a chemist and a chemical engineer in trying to recreate some of these properties that you were just describing?
Yeah, for sensing systems, so to mimic the sensing functions of human skin, we need electronic devices. But the current electronic devices are mostly made with rigid and brittle materials. They are not skin-like at all. That's the first challenge we have to address. But at the same time, it gives us good motivation to think about how we can design molecules that are skin-like, but also at the same time can conduct electricity just as good as metal, or can be semiconducting materials as good as some forms of silicon.
And without getting into too much detail for us non-chemists, what was sort of the fundamental insight that has allowed you to do that?
So basically, we have to first understand what allows molecules, or more precisely polymers, very long chains of molecules. And the first challenge we have to tackle is to understand the fundamental aspects of what makes a molecule to be able to conduct electricity. Because normally polymers, actually in common words, they would be plastics. Typical plastics are insulating materials. They block electricity.
Right.
But in our case, we have to figure out how to make them conduct. So that is a great fundamental challenge. We have to understand various ways of putting different atoms together and which sequence and arrangement to put them together in this long molecular chain. And also at the same time, we have to figure out how to arrange these molecules from the molecular level to nanoscale all the way to a thin piece of film that's actually being used to make devices. And over the years, we were able to gain the fundamental understanding, which allowed us to be able to come up with now skin-like semiconductors, skin-like conductors, skin-like dielectric materials that have good electronic property, but at the same time, we added a new function, either making these electronic materials to be stretchable. Also, we can make them self-healable now, and also even biodegradable. So then these materials are the foundational materials that we need to use to now build sensors, to build integrated circuits, and then we can put them together to make systems to truly mimic our human skin.
And in some cases, if I remember correctly, I mean, you've also exceeded the capacity of the human skin. I mean, obviously our skin has nerves in it, but it's not itself an electrical device. But the sensory abilities of these skin-like electronics you've developed are also really remarkable. Could you just speak for a second to the sensitivity of some of the devices you've built?
Yeah. For example, some of the pressure sensing skin that we have built, they can have ability to sense very, very weak, tiny forces, even better than our human skin. For example, the landing of a butterfly or the resolution of the sensors that we are able to incorporate can also exceed the ability of our human skin to sense different objects. Recently, we built an electronic skin that can be used to sense the entire word of Braille pattern in one touch. With human skin, usually we have to sense one letter at a time to differentiate the different words. So if we integrate more sensors onto our electronic skin, we can also envision potentially sensing an entire sentence just with one touch. So this is just the beginning of thinking about building electronic skin, not only to mimic human function, but also to enhance human function.
Oh, that's incredible. Well, I'd love to talk about some of these specific applications. You know, I brought up this idea of the Luke Skywalker hand, and I understand we're still pretty far away from being able to lose a hand in a lightsaber duel and just pop on a new one and go on our way. But some of the tools that you've been building are really incredible and will help us think about what are some of the potential applications of these materials and these electronics you've been developing. I'm just going to quickly share, I think, a very partial list that'll help give listeners a little bit of a sense of the scope of what you've done. So there's a smart bandage with a conductive hydrogel that supports self-healing. There are heart sensors that adhere like postage stamps to the beating heart to locate atrial fibrillation. There are wireless sensors to monitor the growth of cancerous tumors, non-invasive blood pressure monitors for newborns, which apply your eSkin Concept's ability to feel. Since this is a neuroscience show, I'm obviously particularly interested in the sensors that are involved in touch and communicating with the nervous system. So I wonder if first we could talk about this device you're calling the Mentade, which is sort of a mental health wearable sensor that measures things like stress hormones, heart rate, and changes in skin conductance. And I think the idea is to use it to assess depression and anxiety and other mental health conditions. I think when people first think about this, and certainly when I was first thinking about this, it sort of struck me that, like, don't people know when they're stressed? We can self-report these things. But I was struck by a comparison that you made to the advent of continuous glucose monitors for people with diabetes. I wonder if you could speak to that comparison a little bit.
Yeah, so for diabetes, we can use blood sugar level, and also we can track our food intake and know whether the blood sugar level is too high or too low. But for stress or anxiety, we have some idea of how we feel, but there's no quantitative measure of the level of stress we're experiencing. Currently, we can only ask the patient to rate their stress level in terms of 1 to 10, but that's not a value that actually reflects the exact body response. And so that's why we're developing this mandate that specifically we hope to be able to measure the cortisol level, which has been known to be a stress biomarker, and it can be combined with other physiological measurements such as heart rate variability and skin conductance to determine the level of stress. Actually, this type of measurements and also the idea of using this kind of measurements to hopefully quantify mental state is not something that I came up with, but this is actually through discussions with our colleagues at psychology, psychiatry, and other parts of campus. That's when we learned about this problem, and then that motivated us to adapt our electronic skin to address this very important issue.
Yeah, I could actually see many ways in which that would be valuable. I mean, you can do a questionnaire for a doctor, but that's a one-time response, right? That's how you're feeling at a particular moment in time, or trying to summarize how you've been feeling over the last 2 weeks or the last 6 months, which is very hard. But having continuous data that's coming in all the time, either if you're trying to evaluate whether maybe you have an anxiety disorder and you might need to do something about that, or I could imagine even in our everyday lives. I mean, I had a consultant a while back who was talking about people go in the box in a work environment and people are not communicating well because everyone's stressed out. And so having a way of sort of getting that check-in that maybe people aren't necessarily in the place where they have done the mindfulness meditation practice for years and so on to be in touch with exactly what their stress levels are. But if you have this device that's like, hey, you're getting into a place where maybe you're not thinking straight, or maybe you're going to react in an angry way, you could dial that down a bit. Maybe you need to take a walk. I could imagine that just having something like that could be valuable for people.
Yeah, definitely. Things like chronic stress might be things that we don't even know we're experiencing, and it can have significant long-term impact on our overall health. So this is something that I think this type of device potentially could be very helpful.
Yeah. Well, I want to turn to another application of the technology that you've been working on. So just like the Mentate that you're developing is sensing cortisol in the skin as well as other factors, you've also been developing tools for neuroscientists that can do things like sense the neurotransmitters that the brain uses, like dopamine and serotonin, as well as the electrical signals that neurons and other nervous system cells are sending. And the audience may not know this, but neuroscience just didn't really have great sensors like this until this work, particularly sensors that are soft and can actually go into the brain or into parts of the nervous system that are soft and squishy, and you don't want to be sticking hard electrodes into them. And in fact, we've actually already touched on your work. One of our earlier episodes was with Ernie Huan and Matt McCoy, and Ernie has been using similar types of technology to study the octopus nervous system, where there's no hard bones to attach an electrode to. So you need to have something soft to be sensing what the brain is actually doing. But more broadly, what's your sort of big vision here? How do you envision these sensors being used to advance our understanding of the brain and mental health conditions?
Yeah, so for neurochemical sensing, there have been some sensors that requires injecting certain chemicals into the brain, and then they can be used to label the dopamine or serotonin that's generated in the brain. So for that kind of sensors, they can potentially be used for animals, but very difficult to use on human. For human, there has been things like carbon fiber has been used, but it's very rigid and it can only sense in one particular location. It doesn't allow sensing of the neurochemical generation in multiple locations, maybe within the depths of the brain or in different directions where these chemicals might be generated. So there are limitations, especially for neurochemicals. They're not only generated in the brain, but also actually more than 90% of the serotonin is generated in our guts. And the neurochemicals in the gut can in turn regulate our brain. So it's also important to understand the neurochemical dynamics and how they change over time in the gut. For the gut, there are essentially no tool available for measuring the neurochemical levels because the rigid carbon fiber that's currently available is not possible.
Right. That sounds very uncomfortable.
Right. Yeah, so that's something that we think that the skin-like sensors, actually we make them into, in this case, a one-dimensional string that's like similar to an elastic string that can be readily implanted and be used in the gut. So that offers a very exciting opportunity for us to first to be able to monitor these neurochemicals in the gut, and also potentially to measure simultaneously in the gut and in the brain, and to understand how the neurochemical changes in both places, how they affect each other.
Yeah, the gut-brain axis is such an important area of discovery right now. Well, the last example I wanted to touch on, I think you mentioned a little bit early in our conversation, but this is a recent paper you published in Nature about some of the latest versions of your soft integrated circuits. And these are circuits that can be incredibly tiny, but powerful enough to drive an LED screen, and I think more sensitive than human fingertips. There's this great image with the news story about this paper that came out that we'll link in the show notes, but is a person's fingertip, and on the fingertip is a single sesame seed, and on that sesame seed is this tiny little high-density transistor array with 1,000 transistors in a square millimeter. It's just really, really cool to see. So can you tell us a little bit about this latest version of the technology and some of the ways you're hoping to use it?
Yeah, so integrated circuits are used to make microprocessors and also to switch the images for the displays. And in the case of sensing, if we're going to have a large number of sensors, having the switches, one switch behind each sensor would allow us to significantly reduce the number of wires that we need to access all the sensors. At the same time, this is learning from human skin. Our mechanoreceptors can convert the pressure or temperature into action potential. So basically, the signal is transmitted through pulse train signal through our nerve to get to our brain. The pulse train essentially is using frequency of the pulses to encode the information of high temperature, low temperature, or high pressure, low pressure. This allows the maintaining the signal quality when the signal needs to travel over a long distance. And at the same time, it allows low power computing, essentially. A lot of people are calling the neuromorphic computing, and those are essentially learning from how our brain computes information. So here, these pulse trains are important for that kind of low power computing as well.
So the device is actually directly inspired by the way our nerves send signals through these action potentials that get propagated over long distances without using a lot of energy. That's really cool.
Exactly. So that's why we needed to develop integrated circuits that are also soft as skin so that we can place them right next to the sensors that are distributed either over our hand or along our body, or even for the electrical signal that we record from the brain. They are very, very weak. Also, the neurochemical signal, they are quite weak. So having the integrated circuits will also allow us to amplify such signal right after the measurement.
Wow. So looking ahead 10 to 20 more years, can you paint us a picture of how you could imagine these skin-inspired electronics being integrated into our everyday life? How might we be using these in one day in the future?
Yeah, so maybe 20 years from now, I think actually I'm not thinking that everyone will have a brain probe implanted in their brain, but rather I think if we understand how our brain controls our peripheral organs, then we can use skin-like wearables to perform measurements at the peripheral, whether on the skin, through the skin, or underneath the skin, in the gut, or in other parts of the body. And there will be sensors some are attached to our skin, some may be implanted, or some might be incorporated into the clothes we wear. And they allow us to be able to understand our health from all different levels, from various chemicals or hormone, and we would have the record and be able to track it on its own. And potentially, maybe we don't even have the cell phone with us anymore. It might be a little cube that we put in our pocket. And if we want to see the information about our health, we take it out and then stretch it to any size we want. Or when we are exercising, maybe I stretch it and attach to my hand, and it will just be like a small bandage, and it will display my exercise level or the heart rate and everything. When I'm done, then it already measured the chemicals during exercise, and then I'll take it and let it shrink back to a little cube and put back in my pocket. I think those are things that can very likely happen in the future.
It's a fascinating picture. Well, thank you so much, Zhenan, for coming on the show. This has been a real pleasure.
Thanks for having me.
Thanks again to our guest, Zhenan Bao. Zhenan is the K.K. Lee Professor of Chemical Engineering at Stanford and founding director of eWEAR, the Stanford Wearable Electronics Initiative. We'll include links for you to learn more about her work in the show notes. If you're enjoying the show, please subscribe and share with your friends. It helps us grow as a show and bring more listeners to the frontiers of neuroscience. We'd also love to hear from you. Tell us what you love or what you hate in a comment on your favorite podcast platform, or send us an email at neuronspodcast@stanford.edu. From Our Neurons to Yours is produced by Michael Osborne at 14th Street Studios, with production assistance from Morgan Honecker. Our logo is by Amy Garza. I'm Nicholas Weiler at Stanford's Wu Tsai Neurosciences Institute. We'll see you next time.